Welcome back to the Art of Climate Modeling. To date, we've primarily been focused on design and implementation of global atmospheric modeling systems. Today, we'll be turning our attention towards strategies for evaluating those systems. Lorentz's famous paper on chaotic systems, the same paper that gave rise to the term the butterfly effect, actually emerged from the study of atmospheric motion. Indeed, the atmosphere is an example of a chaotic fluid, one where small perturbations in the system can lead to significant differences in only a few days' time. In atmospheric modeling, the decisions made over the course of the model development cycle also contribute noise to the system, and consequently lead to rapid divergence among modeling systems. This property makes it very difficult to evaluate atmospheric models and ensure their performance is consistent with reality. The spread among different modeling systems, which are individually based on similar physically consistent choices, gives rise to model uncertainty, a range of possible outcomes among GCMs that are in effect solving the same problem. In conducting atmospheric model simulations, there are generally three forms of uncertainty responsible for the spread in the model climatology or state: structural uncertainty, data uncertainty, and parameter uncertainty. Structural uncertainty refers to uncertainty because of the structure of the model. It comes from differences in the choice of the dynamical core, the choice of physical parameterizations, and differences in model resolution, whether horizontal or vertical. Data uncertainty emerges because of differences in the initial data, observational errors resulting in imprecise measurement of the model state, and differences in the boundary data, such as sea surface temperatures in the case of atmosphere-only runs. Parameter uncertainty comes from the choice of different physics tuning parameters, slight differences in the choice of physical constants, and differences in quantities such as explicit diffusion. To limit the number of ways that uncertainty can creep into the model evaluation process, model developers have traditionally employed an evaluation hierarchy. On the left, we have more deterministic tests which are subject to fewer sources of uncertainty. Sometimes, we'll even have access to exact analytical solutions that can be used to quantify model performance. As we move to the right, the resulting model state becomes less deterministic and must be assessed in terms of more statistical measures of performance. For example, for AMIP or fully coupled models, performance is assessed in terms of the patterns of temperature or precipitation over the globe. This diagram was mentioned briefly in Lecture 2, but we'll now explore it in more detail. The most deterministic tests that still capture key physical processes of the atmosphere include shallow water and advection test cases, the former using a set of hydrodynamic equations that are substantially simplified, and the latter dealing with problems related to the movement of moisture or other tracer species. Because these tests primarily consider only 2D flows, the complexities related to atmospheric stratification or vertical boundary conditions are not included. However, one can add complexity by either including some sort of physical parameterization or moving the model to 3D. Many dry dynamical core test cases are available, and many of those have been featured in the popular Dynamical Core Model Intercomparison Project test suite. After dry dynamical core test cases, we again can increase complexity by adding simplified physical parameterizations, such as those related to microphysics, mixing, or radiation. Beyond this, modeling centers typically perform so-called aquaplanet experiments, which simulate a standalone atmosphere with a prescribed lower boundary and no topography. When a land surface is added in, models can then run Atmospheric Model Intercomparison Project, or AMIP tests, which use prescribed sea surface temperatures. Beyond AMIP simulations, the next step is usually fully coupled model simulations. The deformational flow test is a good example of a highly deterministic test case, used for quantifying errors in the scheme that governs tracer transport. In this test case, two blobs of material with high mixing ratio are advected by a flow that deforms them into thin filaments before reversing and depositing them back in their initial position. The differences between the final state and initial state can be used to quantify how much error is introduced by the transport scheme. We can also test different aspects of these schemes, including monotonicity preservation, that is, no artificial introduction of oscillations in the flow. We can also test whether these schemes preserve functional relationships by using multiple tracer fields. For example, if we advect a second field whose mixing ratio is the square of the initial field's mixing ratio, is the scheme able to preserve that quadratic relationship? Properties such as these are valuable when it comes to accurate handling of atmospheric chemistry. After the tracer transport equation, it's common to perform tests of a dynamical core configured for the shallow water equations. These equations incorporate one prognostic variable for air mass and two prognostic variables corresponding to the components of the velocity along the sphere. The simplest such test in this setup uses a geostrophic field, which is a steady solution of the shallow water equations. This configuration is typically run for 5 days, and the final state compared against the initial state under a variety of error metrics. This can then be used to ascertain if errors in the dynamical core converge with resolution, as would be expected. More complicated shallow water test cases then follow, but ones whose solutions are less deterministic. Tests like the Galuski shallow water barotropic instability do not have an analytical solution, but can be compared against high-resolution reference solutions computed with another model. Moving beyond shallow water test cases, we end up in the regime of 3D dry dynamical core test cases. While the shallow water equations are essentially deterministic regardless of the dynamical core employed, design considerations do lead to divergence among 3D dynamical cores. In particular, the upper boundary condition, handled via Rayleigh damping or a model top sponge layer, remains a model design choice of 3D models. Nonetheless, we do expect qualitative agreement among these models, and to a lesser degree, quantitative agreement. One of the most well-known test cases for the 3D dynamical core is the Baroclinic Instability test of Jablonowski and Williamson. A small initial perturbation is added to a baroclinically unstable state in order to trigger a growing instability in the flow. This further leads to the formation of a periodic pattern of growing extratropical cyclones and associated frontal systems. While this test has no analytical solution, quantities like the minimum surface pressure can be used to determine model correctness. As we've seen before, this test can expose some eccentricities related to the dynamical core, including spectral ringing or grid imprinting. It can also uncover instabilities in the model associated with accumulation of energy at the finest grid scales, or other errors in the model formulation. Another popular test of 3D dynamical cores is flow over topography, where a conical mountain is added to an otherwise geostrophically balanced flow. The resulting solution generates a downstream wake of Rossby waves, which eventually propagate globally. Over sufficiently short timescales, these solutions can be compared between dynamical cores. With tests like the Baroclinic instability, invariants like potential entropy or total energy can be measured to first verify that these quantities are approximately conserved, and secondly to ensure that the model is behaving stably. That is, there is no subtle growth of energy over time. These plots show a comparison among schemes employed in a finite volume dynamical core for computing fluxes. While the former tests work for both hydrostatic and non-hydrostatic models, we may also be interested in assessing model performance at scales where non-hydrostatic models diverge from hydrostatic models. To do so, a common strategy is to shrink the radius of the planet until the grid spacing is pushed below 10 kilometers. These are so-called small planet experiments, like the non-hydrostatic mountain wave test case shown here. In order to move our simulations closer to real climate simulations, dry dynamical core test cases are normally augmented with simplified physics parameterizations, whose impacts on the simulation are more easily understood. One such commonly employed test case is the Held-Suarez climatology, which consists of a prescribed analytical heating pattern that is a function of latitude and altitude, along with prescribed surface fluxes and friction. These simulations are normally run for 1,200 days, with the first 200 days discarded as spin-up. Climatological variables are then computed over the 1,000-day analysis period, including zonal averages of zonal velocity, temperature, meridional flux of zonal momentum, and meridional flux of temperature. Plots are then compared with reference simulations to assess model performance. Short-term forecast simulations with simplified physics are also used to examine model performance. One such example is the Reed-Jablonowski tropical cyclone test case. This idealized test case uses an initially axisymmetric vortex in gradient wind balance placed into an environment favorable for tropical cyclone development. The simplified physics parameterizations include surface fluxes, boundary layer turbulence, and condensational heating. A time series showing the growing strength of the TC can then be compared between model dynamical cores. As real physical parameterizations are added to the mix, we end up with 3D aquaplanet experiments. These experiments use prescribed sea surface temperatures and sea ice, zero topography, and the full set of physical parameterizations from the atmospheric model. Because of symmetries present in these simulations, sometimes as little as 1 to 2 years are needed to obtain converged climatological statistics. These plots show zonal mean 3-year zonal wind from 4 GCMs that participated in a multi-model intercomparison of aquaplanet simulations. Many real-world atmospheric features are duplicated in aquaplanet simulations, including moist tropical processes and the waves that carry these systems globally. In the plot on the left, we see characteristic eastward propagating wave packets in the tropics that are present in CAM-FV and CAM-SE simulations, but absent in the CAM-Eulerian runs. Notice the absence of precipitation systems moving to the right and up in these diagrams. On the right, we see plots of rain rate from several different models showing an extreme divergence in rain rates above 40 millimeters per day. Once topography and the land surface are added back into the aquaplanet model, we obtain 3D atmospheric model intercomparison project, or AMIP tests. These tests use all model components except for the ocean and sea ice, both of which are prescribed. Tests can be run for several years to decades depending on the processes or features being examined. To see some more cool videos of AMIP class simulations, check out the links here. These show common atmospheric features, including atmospheric rivers and tropical cyclones in models with quarter-degree grid spacing. And the bottom link even shows a simulation at 4-kilometer global grid spacing conducted in the MPAS dynamical core. After AMIP simulations, we move to fully coupled simulations of the Earth system that include all component models. Fully coupled simulations of past time periods are typically compared against observational data, including remotely sensed or in situ measurements. However, differences between simulations can be hard to understand or trace because of the complicated web of interactions within the full modeling system. Extensive international intercomparison efforts, including the Coupled Model Intercomparison Project, or CMIP, have been employed for the past 30 years to compare results from fully coupled model simulations. Results from these simulations have further fed into the Intergovernmental Panel on Climate Change, or IPCC, assessment reports. To facilitate comparison of these models, standard experiments have been designed as part of CMIP to investigate model performance. For these classes of simulations that are less deterministic, particularly AMIP and CMIP class, ensembles may be needed to ensure that the statistical properties of the model are being fairly evaluated. Put simply, ensembles are collections of simulations with most parameters held constant. They are employed to investigate sensitivity of different model or simulation choices. Perturbed parameter ensembles consider variations in the tuning factors for physical parameterizations or the dynamical core diffusion coefficients. Recall that parameterization tuning parameters are not necessarily limited to one physically consistent value, but instead there is a general range of possible values. Subsequently, more comprehensive sampling of the space of possible parameterization tuning parameters allows a modeler to investigate sensitivity to these parameters. Initial data and boundary value ensembles include simulations conducted with small variations in the initial data, topography, or sea surface temperatures. As a consequence of the inherently chaotic nature of the atmosphere, these small variations can lend to effectively different climatologies in only a few days. Finally, multimodal ensembles involve different models run on the same experiment, allowing one to explore how the model affects any conclusions one can draw. As discussed in the last lecture, there are generally dozens or more model parameters, each of which can take on multiple physically reasonable values. In this case, physically reasonable values refer to those that are not contrary to the assumptions or approximations made in the design of the parameterization. It does not imply that the resulting model simulation is necessarily physically consistent. To perform a perturbed physics ensemble, expert guidance is typically needed to select low and high estimates of the parameters being explored, plus some reasonable middle ground estimate. Values for these parameters in each simulation can then be selected from the extremes of each parameter, or by simply picking randomly from the range. As models become more complex, a growing need for confidence in our model results has emerged. As a result, the study of model intercomparison and evaluation has become a growing scientific discipline. While the concept of success when it comes to model development may be obvious qualitatively, that is, models should behave in a manner analogous to the way the real world operates, both measuring and quantifying success remains difficult. One can define countless metrics or diagnostics related to the fields output by a modeling system, but with limited time and computational power, it is inevitably left in the hands of the model user to define which quantities are most important to them. With that said, there are certain basic principles that should be followed in evaluating models. For instance, when models are being used for scientific purposes, it's important to focus on evaluation tools that build credibility in the conclusions being drawn, or those that provide insight into the sources of biases in models. In terms of model development, it's important to build a hierarchy of approaches for validation so that we can ensure the model is behaving correctly in the most deterministic test cases before we consider model performance in the statistical regime. Deterministic tests are also relatively cheap compared to statistical tests, which can require months to years of simulation. As models become more complex and more components added, there are more ways for the model to fail. And in these complex, intertwined modeling systems, identifying the reason for a model failure is very difficult. It's far easier to ensure correctness at the component level, then build upwards towards a fully coupled modeling system. With that said, although we have made great advances in the development of these modeling systems, it has subsequently become easier to introduce bugs or assumptions that degrade model performance quickly. This means it is more challenging than ever to improve the performance of individual modeling systems. We now turn our attention away from the evaluation hierarchy and discuss some of the data products and tools that can be used to evaluate models. That is, quantifying model performance requires us to have a target to evaluate against. Observational data provides that target, and it is drawn directly from real-world observations. But which observational data sets are available for this purpose? A wide variety of observational data products are available from all over the Earth, often containing a wide variety of relevant variables. Remotely sensed data is drawn from a vast array of satellites continuously transmitting observations back to the Earth, with most operated by NASA or the ESA. In situ or remotely sensed measurements are also taken by research and commercial aircraft, radiosondes, weather balloons, and radar. While at the ground level we have weather stations, rain gauges, buoys, and ships. All of this data provides immense value when it comes to model evaluation. Observational data products can be broadly classified into direct satellite measurements, station data, Lagrangian data, and gridded products. Direct satellite outputs include a variety of remotely observed data from orbiting satellites such as NASA's TRMM, GOES, MODIS, or CloudSat. These include up-to-date measurements of precipitation, wind speeds, sea surface temperatures, and other fields over large geographical areas. However, using this data directly can be difficult because data are often only available as unstructured ASCII or custom binary files, often employ uncommon grid projections because of how the measurements are taken, and often contain missing data outside of the swath. Station data include, for instance, in situ weather station data or snow data measured over a long time at a single point. Because of geographical limitations, stations are not located on a standard grid, which can affect their utility for certain studies. For example, few weather station observations are available at high altitude. Additionally, there are significant differences between pointwise measurements and grid cell averages, so one needs to be careful when using these products to evaluate GCM performance. Lagrangian data include weather balloons, aircrafts, buoys, or mobile measurement stations. These types of data are even more difficult to deal with because the measurement position changes in time and space. Although it's often desirable to use the most unadulterated forms of observational data, reprocessed products are available that can make observational data look more like model data. Using direct observations, various models or interpolation schemes have been developed to remove missing data and interpolate the data to standard rectilinear grids. For example, various gridded climate data products are available, including PRISM and CPC datasets, which include temperatures and precipitation with regular spacing across the United States. Additionally, a variety of reanalysis data products are available, including ERA 5, CFSR, JRA 55, MERA 2, and many others. We've already mentioned reanalysis data several times throughout this course. However, given how important reanalysis data is for model evaluation, it's important to understand how it is created. Put simply, reanalysis is a systematic approach for producing complete gridded observational datasets that can subsequently be used in research and model evaluation. These products are produced by forcing a model to match observations via data assimilation. That is, digesting a variety of different observational and data products that are staggered in space and time, and adjusting the model state to match those observations and data closely. Given that the model has been designed to maintain basic physical principles and processes, it provides a physically consistent way of filling in gaps in the dataset. However, as we know, no model is perfect, and the reanalysis product will inevitably inherit some of the biases of the model being employed. More information on available data products can be found at the 2 links provided below. Data assimilation occurs at regular intervals in reanalysis products, depending on the temporal frequency of the observational data. Curated observations of the state taken from satellite observations, station-based measurements, and Lagrangian data all contribute to the forcing data employed. Essentially, at each time step, the observational data is used to devise a gridded state, and then the model is run forward in forecast mode to fill in gaps in time. To give an example, ERA 5 reanalysis uses a 12-hour window between assimilation operations. Rapid growth in the number of observations produced on a regular basis has meant reanalysis must frequently adapt its algorithms to digest an increasing number of data points. The plot on the right here shows the number of observations taken into the MERA 2 reanalysis product. The number of data points has increased dramatically from around 100,000 in 1980 to over 5 million today. Because reanalysis products are highly dependent on the broad spatial coverage provided by satellite data, most of the highest quality and most frequently employed datasets start only after the dawn of the satellite era in 1979. Today, there are dozens of global reanalysis datasets available covering a variety of time periods and at different temporal and spatial resolutions. On this slide, we see details of some of the most popular U.S. products, including the NOAA NCEP reanalyses and the NASA MERA product line. More broadly, the European Center for Medium-Range Weather Forecasts produces some of the most widely used reanalysis products, listed at the top of this slide. Additionally, several high-quality reanalysis products are produced by the Japanese Meteorological Agency, with both standalone atmospheric models and fully coupled modeling systems. All right, let's now briefly turn our attention to the tools that are available to assist with model evaluation. You may even consider using some of these tools in your own work. Once you have an observational dataset in hand, it's simple enough to leverage the variety of software libraries for analysis and visualization. Some common examples include Python's Xarray and Matplotlib libraries, the NCAR command language, and NetCDF operators. Here we see a simple plot showing CAM precipitation and GPCP precipitation measurements side by side, produced by NCL. Certainly, not every plot needs to be custom designed. To assist with the evaluation of model results, a comprehensive set of metrics and diagnostics from CAM are available through a package developed by the Atmospheric Model Working Group, or AMWG. The package is known as AMWG Diagnostics. It includes standard scripts for computing climatologies, including global means, zonal means, latitude-longitude plots, annual cycles, clouds, and other relevant plots. Here we see some examples of plots produced by AMWG Diagnostics, including global plots of zonal mean temperature on the left and polar plots of sea level pressure on the right. Each of these sets of plots includes both model results and observations, along with the differences between them. Another common evaluation tool is a Taylor diagram, which allows information on spatial error and correlation to be compressed into a single plot. Multiple variables can then be displayed within the diagram. Here, the Taylor diagram includes sea level pressure, cloud forcing, precipitation, temperature, winds, and humidity from 3 different datasets. Portrait plots are a way of displaying extensive detail on metric scores for various models in a compact way that allow for easy comparison. Models are ranked with negative scores if they perform better than the mean model, and positive scores if they perform worse. Each cell is broken up into 4 triangles, with each quadrant referring to a different season of the year. Variables being evaluated are listed along the y-axis, here including geopotential height, meridional velocity, zonal velocity, temperature, radiation, and precipitation, while models are laid out on the x-axis. Plots such as these are easily generated with packages such as the PCMDI metrics package, or PMP. Finally, plots like stoplight diagrams can be used to evaluate our model results. On the left-hand side, we see the absolute score of the model for a variety of metrics, with red, yellow, and green corresponding to poor, moderate, and good performance, respectively. The right plot, on the other hand, shows the relative score, that is, how the system performs compared with other systems. Again, models are laid out along the x-axis, while metrics are along the vertical axis. This particular plot is produced using the ILAM Land Model Evaluation tool. Alright, that wraps up our discussion for today on model intercomparison and evaluation. Hopefully it has provided some insight into how we ensure our models are correct, credible, and representative of reality.